So this is what he sent me today in the morning. So Fabian was born in 1919 in Palatina, Germany. He grew up in a small town called Landau. And so now we do a big step, like 20 years later. He did his master and bachelor studies in Karlsruhe at the KIT. Then he did a PhD at Technical University of Vienna with Martin Neulenburg. And then he is currently doing like a 1-year postdoc here. And he just received a very prestigious Schrödinger fellowship, I think it's called, or Schrödinger grant.
Yeah, they call it fellowship. It's a stipend, I guess that's why the name is chosen that way.
So it is comparable from the career stage with the Rubicon, but it's for 3 years. And 2 of them, he made the horrible mistake with spending with us. So you will see him a few more times, especially after Corona. And he just got the letter this week. So it's really this week is still a good week to congratulate us on him. Unfortunately, one of those, the Austrian, they're more clever. He has to come back for 1 year. So at some point, unfortunately, he has to leave. And before he gives the talk, I wanted to say something maybe more personal about it. So that this question that he answered, I think I heard like 10 years ago, the first time being asked, and it's like an open question, which was open for probably 30 years. Fabian, is this correct?
Yeah, since 89 it was regarded open.
So since 89, so that's now 21 years. And it is a question from graph drawing, but really people from lots of different fields have worked on this. So this is not a niche problem. And the person who asked the question also found the answer in parallel 1 year before, but did not mention it or publish it. So this is a very unfortunate story of work going on in parallel, but it does make it a less important and astounding result. So I think it's really, really great work. And with having said this, now Fabian, you're under pressure to impress everyone. I also want to say something else. Albert was sharing the first block, and I will mainly share the second block. So from now on, you have to deal with me. I'm sorry. And I will not change so much. The only thing is I want to encourage everyone to switch on their camera, because it's really nice for the speaker to see what reactions they get. If something is understood, is not understood. Otherwise, they're just talking to a black screen. For all the people who are teaching, you know the situation. But of course, we will not force anyone to switch on their camera. I just want to highly encourage it. And of course, I will keep my camera switched on. And yes, Fabian, I mute myself. And you have one question, Fabian. Do you want to have questions in the chat after the talk or during the talk?
Just ask question whenever you want to.
Okay.
And probably, if I saw it correctly, this is the first time I give a talk over Teams. Better interrupt me via voice, because I don't know if I actually see the chat somehow.
Okay. I will look at the chat.
Yeah.
And as you heard it, questions during the talk are also welcome. Yeah. Okay. Then I mute myself, and here you go.
Okay. So, yes. Thanks a lot, Till, for the very nice introduction. And yeah, so I guess you can see the slide, just checking, since I had to change setup a bit. Good. Yeah, this is work that is titled, also in the paper, 4 pages are indeed necessary for planar graphs. And this is work that, as Till hinted on, somehow is looked into a lot. This problem is looked into a lot from graph drawing people, so researchers that are interested in drawing graphs in very general terms. But it relates heavily just also to any partial order problem, any ordering question, really. And also, if you open the Wikipedia page of the problem name that you will get to know in a little bit, you will see that it has a lot of application. Since I work in none of these, I cannot really tell you much about it. I will introduce you with a little example that maybe gives you an idea of where this could be applied. And with that said, yeah, my name is Fabian Klute. I recently joined Utrecht University, as mentioned, and this is joint work with researchers from quite a few institutions. So once we have the university in Tübingen, two people who have really worked a long time in this problem. And I think for them it was very nice that they found the answer also. And Sergei Pupirev from Facebook, Chrysanthi Raftopoulou from the University in Athens, and Thorsten Uckert from the KIT in Karlsruhe. So let's look at what are we actually looking into as a problem here. So imagine you stand at an intersection. So this is some traffic intersection, a classic four-way, and there's a car coming, and you are maybe sitting in that car. Then, well, you can go these three directions, right? In general, in most intersections that are there in the world, you can go to the left, straight, or to the right. And, well, you might not be alone at the intersection, but there might be a second car. And now what you really want to avoid here is to crash into the other car. This would be really undesirable to do that because it's probably quite expensive or even risky to your life. And now, how can we design basically traffic lights and make them switch in a manner and cycle or schedule them in a manner such that no two cars ever are in the chance of colliding, but that the paths are always clear? And one way to find such a scheduling can be done using the principal problem that we are interested in here. So let's abstract a little bit here. We will just represent these streets with vertices in a graph. So the street of this bottommost car that it comes from is one vertex, and the three streets it can go to are also vertices here now. And we connect them with edges, since I can go with this car to the left, straight up, or to the right. And now, well, there might be up to 4 cars here, really. And now we just introduce vertices for all of them and do the same connections. And we obtain this graph. And now note that since the geography tells us where these nodes are, so we get an ordering of them. They are somehow ordered around the cycle. Or you can also, and that we will do in the rest of the talk, think of them ordered along a line, just a straight line. And the vertices then go between these, the edges then go between these vertices and create crossings. And these crossings are just forced to you by ordering the vertices in this manner. But now you're interested in finding an assignment of these edges, if you think about them as, well, where can the car go, such that no two cross. Because if they can cross, and if the traffic light is green at the same time, then we might get a collision of the cars. So here's one little observation. You can actually, all these right turns, you can have just always. This can actually be always green. And if you ever drove in the US, you might know that you can always turn right in the US. This is actually kind of why you can never intersect another car. And now we just continue with this color scheming, really. And we say, well, let's see, these two horizontal and these two vertical lines that the cars could drive, we have to color differently. So the red edges, the red ways of driving would be one cycle of the traffic lights. And then the green ones would be another one. And now really all we need to do is do 2 more cycles here. And we see, well, this whole intersection can be scheduled, the traffic lights can be scheduled with 4 cycles such that it never leads to an intersection and hence never to a collision. So you can see kind of traffic scheduling could be seen as an application of what we are going to talk today. Because what are we interested in? It's so-called book embeddings. Book embeddings have been around since a long time. And the very rough idea is really, as we've seen on the slide before, you find an ordering of the vertices, and now you can just think of them on the spine. And you're interested in drawing the edges as these kind of arcs. And you basically take the spine, and you can see that there are immediately 2 ways to do this, well, to the left or to the right of the spine. And you can think of these half planes as pages. And this is also kind of hinted here with this little rectangle, that this is one page. And this is where the name comes from, book embeddings, because what we really do is embedding graphs into pages of a book. So if we kind of draw this with 3 pages now, you see that, well, we have 3 half planes, and they all go are hinged on the spine. So you kind of lose a bit the obvious thing that, well, you can draw them to the left and to the right of the spine, but it's really just you add more half planes along the spine. They are all hinged on it, so you can imagine why this relates to a book. And now always the question is, if I give them some graph, what can I really do? What are my degrees of freedoms here? Well, I can find an ordering of the vertices, and I can tell an edge in which page it should be. So if we look at the graph in the bottom left, this is a K5, a complete graph on 5 vertices, and we want to embed it in a book. Then we have to pick some ordering of the vertices. Here, for example, it's white, orange, green, blue, and then purplish. And then we have to embed the edges on pages. And what we find here is that 3 pages are sufficient. So if I do 3 pages, I will not have any crossing in any page. And this is the key requirement for the book embedding problem. This relates, there's different versions of these kind of linear ordering problems where you might also allow crossings or not. But in our problem here, really, we will never have crossings on any page. There will never be any. And then the optimization question or decision question is really to ask how many pages are sufficient and how many do I sometimes need? So here we see, well, for the K5, apparently 3 pages are sufficient to find an embedding, and actually we also need them. So we cannot get around that really. Okay, there was a second term in the title of this talk. Well, there was the book embedding didn't actually appear, but the pages did. The other term was planar graphs. Just as a quick recap, what are planar graphs? A planar graph is simply the graph that I can draw in the plane without any crossings. And one can probably claim that planar graphs are one of the most widely studied classes of graphs in general, in graph theory, but also in graph algorithms. And we know a great deal about them. So naturally, people started also, when book embeddings came up, to ask, well, how many pages do we need for planar graphs actually? And so this is the question we are going to tackle here. How many pages do we require for planar graphs? And now let's go into a very simple first lower bound. Is 1 page maybe also always sufficient? So do all planar graphs fit into 1 page? And the answer is no. And why is that the case? Well, if you look at this K4 drawn here in its non-crossing configuration, and you see, well, it's a planar graph. That's nice. But now, no matter how you maybe draw this, take this red vertex and pull it out of this triangle, you will create a crossing. And if you now think about, well, take this ordering as we did with the traffic circle to a line and put it on the line, this crossing will remain there. You will still have a crossing. And what does it mean? It does never fit on 1 page. No matter where you put the red vertex, you will always produce a crossing, hence you need 2 pages. So we already know, well, planar graphs sometimes need 2 pages. Okay. Now, as I said already, these problems, these book embeddings have been around since a long time. People trace it back even to the 60s, but the term properly was coined in the 70s. And we just saw, well, 2 pages are sometimes required, and it's a rather straightforward result. What about how many pages always suffice? In '84, Bus and Shor showed the first bound of that kind, and they showed that 9 pages are enough, defeating back then quite a set of conjectures that said, well, no, you will need some linear number of pages in the amount of edges or vertices. So this was back then a surprising result, that a constant number of pages is always sufficient. So any planar graph can be drawn using at most 9 pages. And in the same year, Heath improved this already to 7 pages. And then '89, Yannakakis improved this bound again to 4. And 4 is very low because we saw, well, 2 we can easily require, 2 might be necessary. And what about 3? Do we know that 3 is sometimes required? And actually, already in '75, Goldner and Harari had found a planar non-Hamiltonian graph. And for technical reasons, these require always 3 pages. So you can show that this cannot fit into 2 pages. And well, then we know 3 pages are required. But this is kind of then was the state of the art in '89. We knew 3 pages are required and 4 pages are always sufficient. And then in 2020, we demonstrated that there are planar graphs needing 4 pages, and Yannakakis independently also published fixed proof of a sketch that was back then published in one write-up of himself that, well, was never formally finished, so to say. So researchers tried for a long time to complete this sketch. They never managed, and Yannakakis published the complete proof also independently of us at the same time. Okay. So now, how does this 3-page lower bound look? Is this very complicated? Is this a humongous graph that you have to look at? Actually not. It's a rather simple, small graph. And you can just actually exhaustively still check that, well, this is fine. It takes you a while, but it's okay. Now, what about 4 pages? So what do we really need here? And how much more complicated will it get? Well, we need to find a planar graph that for any ordering of its vertices, so for any chosen linear ordering of them, and any 3-page assignment of its edges, we find a crossing on some of the page, on one of the page. Because that will mean that we need an additional page. But from Yanakake's result, we know how to embed it into 4 pages. We have an algorithm to do that actually in linear time. It's very complicated, but in principle, we know how to do this rather fast. So let's go into it. Is the 4-page case as easy as the 3-page case? Obviously not. So here you see a graph. It's still quite moderately sized. It fits on the slide easily. And the slide is titled The Basic Gadget. And as you will see, this is really just the basic, tiniest building block of what we're going to construct, because the graph that we require to actually show that 4 pages are sometimes necessary is humongous. So this is the basic gadget. I will not go into any of the structure really of how this little graph is built. But how do we show now, or how do we use it? So this graph basically we found using some intuition on which graphs should be hard to embed into the 3 pages, if 3 pages was the right answer. And using that intuition and then putting a lot of restrictions on this graph and tossing it into a SAT formulation of that problem, the SAT solver will say no or yes. So it's important to remark, if you toss this graph without any restrictions into a SAT solver that computes you the best possible book embedding, it will say, well, 3 pages are fine. You can do this thing in 3 pages. It's okay. But if you start to put restrictions of the form, well, we want AB to be the 2 leftmost vertices in the ordering, or we want all the edges of A coming to be on the first page and all the edges of B coming to be on the second page, we start to understand under which requirements this graph will not fit on 3 pages. And this is really a combination then of having the right intuition, what you have to actually ask the SAT solver, because you cannot iterate through all possible restrictions really, and just output all of them for which it fails, and the intuition of and the SAT solver in the end as well, because we would be not able to really check these requirements. It's very cumbersome to check them while you're exploring, is this graph helpful? Okay. So this little graph will be from now on red. And we are going to use this graph now a bunch into building our big graph that we actually want. And this first graph now we are going to build that has some nicer properties is the graph Q. So let's zoom out a bit and let's use a bunch of these red graphs. In fact, we will use 9 of them. And we will put them in kind of a parallel looking structure where we copy paste them underneath. And the vertices get identified at this vertex marked T1, and then below at what would be T2, what would be T3, and so on. And in total, you will see 9 copies of this graph in this one gadget. Well, this is already getting quite large. Is this sufficient? No, not at all. This graph fits still on 3 pages. But actually, this now, I will mark it blue graph. We only need to use some assumptions, not too many anymore. It's a bit too many and too technical to really put it in this talk, but it's rather simpler assumptions. So it's assumptions of the form that I said, but not too many. We don't need to go crazy and say, well, this one little blue vertex up there in the left is at position 5 in the ordering. But we can put rather general assumptions. And here then what I said before really comes into play. We combine this human intuition on what assumptions are good with the SAT solver power to check them and find the things that we need then, the restrictions that we need to enforce to say, well, this cannot work. And now, how does this work? How do we get to a point where we can actually reason about, well, we want to get these restrictions? Because from now on, the goal is always build a graph such that this blue graph ends up in a certain configuration that we know will fail. So how do we get there? Well, we again forget about a bit of labels here because we will zoom out again. And now we put this graph into something that rather looks like the blue graph again, but here we just take a bunch of copies of Q of the blue graph and put them on these 2 black vertices and put them in kind of a parallel structure. So all of this graph is actually biconnected at these two black vertices, and if you take them out, the whole thing falls apart into these copies. And how many do we take there to get this green graph, G uppercase N? Well, this many. So this starts to look quite big, I guess. And this is where then combinatorics comes in. And this is kind of the third ingredient you need to get these kind of proofs, where you really need a big graph, a big structure to get rid of, or to find a way to prove that, well, this doesn't fit on 3 pages or similar results. So, and why do we need that many? Well, as I said, we know some restrictions under which Q will fail, under which Q cannot be embedded into 3 pages. And to get them, we just use the law of large numbers, where if we have enough of them, a lot of them will be in some configuration. And let's go a little bit into that. What do we want? We want many copies of Q. So if you think of this green thing just as many, many copies of Q that are stacked below each other, where the vertices are in the same relative order and where the edges are on the same pages. So we basically want to say a statement like, well, this graph Gn, we have it. And because there are so many of this, we find some certain structure in there. Or to illustrate it with just pairs, imagine there's some red and blue vertex, and you really have just 2 ways to order them, right? It can be red before blue or blue before red, but nothing else. This is the 2 ways to order these. And now if you take a bunch of them, so here we have a bunch of pairs of these vertices, then you can look and one will be in the majority. One, either red before blue or blue before red, will be in the majority. And in this example, if I remember correctly, red before blue is in the majority. So if we want, for example, we need the structure that 3 pairs are red and blue in this ordering, or blue and red, then we just take 5 pairs and 3 of them will be, we can assume that 3 of them will be in this structure. And this allows us to assume that many, many of these Q copies are in some way embedded in our 3-page book embedding, if it would exist. And then we can reason about these and refute the statement that this is a valid embedding only for these, assuming these very strong properties. And this is how we get basically then what the SAT solver confirmed us. Well, this you want to find for it to be broken. This is how we get there. And
Can
this
I
is
interrupt you for a minute?
Yes, please.
So what is the kappa?
Sorry. The kappa will be constant that you determine in the proof. In the end, it will be 28. Okay. It is basically a constant that comes out of the proof. Sorry, I forgot to mention that. That is required by how we argue in the case distinction that, of course, follows this. Yeah, thanks. And now the other wing we know. So we know now some vertices are in some relative order and some edges are on same pages. Very nice. But this is not quite enough. So we basically need to go again 1 step more. Sorry, I forgot something. So let's look at how many copies we have here. And what we will see is that basically this formula, the n factorial, is just, well, these are all vertex orderings that we can have. And the 3 to the m is just, well, all edge to page assignments. So really what we said here, well, take Q so often that every possible embedding is there. And then there are kappa many of these through the 3p. So we have enough of them to make our assumptions. And why is this 3p actually there? Well, this is because we also want that these copies of Q, that between them certain restrictions apply. Particularly, we want that pairs of vertices that are independent, so they're in 2 different copies of Q, that these form something called a rainbow, a necklace, or a twist. I will just quickly show you what that is on a later slide. And to get these are more restrictions on the monotonicity, so to say, of the ordering. So for this, we use Addo-Shekera's theorem, basically, to find a nice monotonely ordered set of vertices. This is more a bit of technical detail, and it's kind of harder to illustrate how this works. And now what comes after this, so you build this humongous graph, and now you really just want to reason about this little gadget, and you can now comfortably assume that a couple of them will be in some nice configuration that you can work with. And suddenly, well, we have to start doing cases. And there will be 2 main cases of this whole proof. One of them is that or this should be a yellow vertex, not a brown vertex, that this blue and this yellow vertex are on different sides of the gray and green vertex, which are these big black vertices from before, or they are on the same side. And this is true for kappa configurations. And you see, we can then already start to assume certain things. So for example, in case 2, we know from the SAT server that then these two edges have to be on one page and on the other page for this to ever be a 3-page book embedding. And well, then we do this assuming, well, we have many of these. So particularly many of our arguments deal with kappa being 3. So we would have 3 copies like this and then start to reason about this. And reasoning about this means we assume some partial ordering of these vertices and then look for structures that cannot happen or that now have to happen, but that cannot happen. And what are these structures? We already saw their names. It's some rainbow, necklace, and twists. And this is really the furthest I will go into any detail. So what we want to often find is the most comfortable thing to find is a twist, because a twist is, well, a k-twist is k pairwise intersecting edges. So clearly, if you want to have ever a 3-page book embedding of any graph, you cannot have a 4 twist in the ordering, because that would just mean that 4 edges pairwise intersect, hence requiring 4 pairs. And a rainbow and a necklace are 2 rather nice planar structures, so they themselves will not be any harm to us. But building from them, we can find the other forbidden configurations, and that's really all the things we look for. These are the kind of configurations we aim to find by drilling deeper and deeper down into this ordering, where we can assume, because we have so many copies of this graph Q, that, well, they are nicely, or they're badly ordered, such that we find one of these forbidden configurations. And this is then rather tedious work and just requires you to go through many and many cases. We just saw, well, there are 2 main cases. These all split into many forbidden configurations. And in the end, you have 3-4 pages of pure case distinction where you just say, assume this ordering, assume this ordering, assume this ordering, and show, well, we find such a twist or any other forbidden configurations deep down in the embedding. Okay, and now just to tell you how really big this graph is, this was not everything. This GN is the main tool we work with. But in actuality, we make it even bigger. So what happens here is we take this graph, we take one of these red graphs again, but a new copy of it, that's why it's marked lila, and just one. And now this edge in the middle between these 2 green vertices, we actually replace it with this big graph GN. And then we embed this again into these 9 copies. And we put this again in the same manner into this parallel structure to obtain the final graph. And I hope that you believe me that this we require. This is not just because we like to build a humongous graph and then, well, everything follows. We actually need this to get the proof to work. This is really then the final form of the graph. And now, yes?
Fabian?
Yes?
This is a finite-sized graph, right?
This is still finite, yes. I will now tell you how big it is, just to brag how big of a graph we built. So how big is this graph actually? It's not infinite. It's hard to write down in the universe. We would quite run out of atoms, but that's okay. So how big is this little red graph up there? It's just 42 vertices, 120 edges. And since we identify a bunch of them along the way, it's actually 39 vertices and 117 edges. This is rather small still. One can work with this. It's easy. Now we bunch 9 of them together, so we get actually 39 times 9 and 179 times 9. So we end up with some 350 vertices and 1,000 edges. Still, this graph one can work with. And now, what is this green graph? Well, now we have seen everything why we have it there, and let's plug in the numbers. So if we compute this P, this is really all pairs that we can have between these Q graphs, because remember, we want this kind of monotonicity properties where we find nice necklaces, rainbows, or twists. And to get them, we have to argue that there are enough between the Qs of the same edge. So kind of the same principal edge in different copies. And this will just come out to 62,000. And then computing this N, we end up with a number that is 10 to the 272,513. Which is well beyond anything that you can comfortably reason about in a human perceptible way. At least I can't, but it's finite. It's not endless. And then Gn itself, of course, has n times 350 and n times 1,000 of these vertices and edges. And now, if we look at this, well, we do this 9 times again. And then actually our final graph really consists of q taken 9n squared plus n times. So we end up with something like 10 to the 545,000 vertices and edges. And I hope I could convince you that we didn't do this just because we had fun constructing such a big graph, but we needed to make arguments work. We needed to get our toolbox running. So
you're claiming you didn't have fun constructing such a big graph?
We had fun constructing such a big graph. It's definitely the biggest graph I have ever been part in constructing. And now, of course, the question is, do you have anything smaller? Because as I said before, we used subsolvers to get to reason about this smaller gadgets, to find restrictions, to confirm restrictions that we know, well, should break this. And since they are on such a small graph, we hope that we can turn them into combinatorial proofs. Until the deadlines, we didn't manage to. But what we also found while exploring, well, we found actually a smaller graph. So this is a graph that doesn't fit on 3 pages either, and this is the whole graph. And it fits on this slide. So this is the whole thing. It has a few hundred and I think 1,000, few hundred vertices and I think 1,000 something edges. And it's nearly the graph that we saw as this little red graph always, just copy pasted together in a ring where we use these big black vertices, the upper vertices and the lower vertices of this red graph and connect them in a ring. And well, this thing, according to the subsolvers, also doesn't fit on 3 pages. But proving just for this graph that it doesn't fit on 3 pages by hand on paper would be very tedious. You have no real grasp on the arguments. You would just really need to go through, well, where is everything? But we cannot assume any nice properties like, well, we have 3 copies of this graph Q that are in this ordering and where the edges are on these and these pages. So all these arguments break down. But still, of course, in our proof, we use SUT as a tool to say, well, this little graph, assuming this and this and this, doesn't fit on 3 pages. So we have a semi-combinatorial proof, you could say. This would be a fully automatic proof that just does SUT solvers. And actually, Yannakakis' completed paper is a fully combinatorial proof. And now one can argue or go into this debate or basically, which of it is the better proof? What counts as proof here? And I guess this is, since ever the 4-color theorem was proven, is an open question to what does count as proof. But just to illustrate you how SUT solvers actually can help in a combinatorial proof to get to a point where, in my opinion at least, the gadgets that you reason about using the automatic methods are small enough that one can believably claim, well, this is fine, this is okay. While for such a bigger graph like it's displayed on this slide, it would be very hard to say, well, you did everything correct and the SUT solver is just right. But I guess that's a topic of discussion in the end. And with that, I also already come to the end of the talk and just give a bit of an outlook where we go from here for people who maybe know a bit more about this kind of problem. So what would be the next steps? So now we know that, well, every planar graph, there are planar graphs that require 4 pages. And we also understand planar graphs fitting into 2 pages rather well. We know that they are actually just the sub-Hamiltonian planar graphs. And now we would be really interested, what are some 3-page embeddable graphs? We know the 3 trees are among them, but there are 2 more categories that are so far unexplored, planar Laman graphs and planar graphs with some certain bounded degree. And then also another direction that now becomes more interesting also since breakthrough result last year of Thorsten Ueckert, who is also in these papers, and other authors that showed that the Q number of planar graphs is bounded. So the Q number or the Q embedding of a graph is a similar formulated problem where you order your vertices along a line, but now you want the edges to intersect. So it's kind of the dual problem, one could say, or it's like the problem where we exactly drop the planarity restriction, but we forbid actually nestings of edges. And we now know 49 Qs are sufficient. We know 4 stacks are sufficient. What is if we take a mixed layout where we take the spine and each page can be either a stack, and the stack is nothing else than 1 page in our book embedding, and the other page to be a Q. And then the question would be, how many stacks and how many Qs do we need for every planar graph? And we know already that 1 stack and 1 Q is not enough. but we don't know much more. We don't know if 2 stacks and 2 queues are sufficient or not. And with that, I thank for your attention, and I hope I could show you a bit when you read this humongous, that there was some proof that uses some humongous object, some humongous piece, why it's there. Why do we need such a big structure?
Okay, thank you, Fabian, for your talk. Yeah, interesting to have such huge graphs. Maybe to your disappointment, I went regularly to the combinatoric seminar in Berlin where they studied Ramsey numbers, and
yes.
I'm not impressed. It's just
No.
You see this at some point popping up all over the place.
Yes. No, that's very true. I was visiting in Waterloo last beginning of this year and was visiting a seminar on graph coloring. And I think 10 to the 500,000 for them would be the base case.
Yes.
That's very true.
There was a question in the
yes.
by Jurian who asked about the proof by Yanakakis. Could
yes.
you comment on this?
The proof by Yanakakis leads to a graph family that is rather, in some sense, similar. And to my knowledge, so as a disclaimer, I have not studied this proof completely because I was very busy also finishing my dissertation and applying for this project, etc., etc. So I can only comment on it superficially. The biggest difference is really that it is a full combinatorial proof. But it uses a very similar style of graph. So these kind of very graphs that have a lot of triangles that we stellate, it's called. So we put a vertex and connect it to all 3 vertices of that triangle. These are the problematic ones. Taking just this doesn't work because 3 trees actually surprisingly fit on 3 pages. That's rather surprising results from some years ago. But it is along those lines, and it then uses a very similar way of arguing. You just have enough copies of this in some kind of structure, and you find parts of this ordering that breaks in a very similar manner. But that's everything I can really comment on it, since I didn't have any time to properly read it.
Okay, thank you.
So he basically starts from a different primitive, and then he starts to also put these copies so that you get this. But he also looks. Does he also have this big factor where you say, well, this is for the number of orderings, this is for the number, because you would expect that a trick like that would be reusable in his setting.
Yes. I'm without knowing this, I'm pretty confident in claiming that he will do something like this to have enough copies to argue about. And the sketch was so the sketch that he had in his original publication very much is along those lines. But the problem was that basically these base gadgets weren't defined. They were just left as blanks, and nobody knew how to fill them in. So nobody had these gadgets in hand. And also throughout the 90s and 2000s, nobody was able to find them.
Right.
Okay. Do we have more questions? I see no more questions. Then or Julian, do you have another question? No? Okay, I guess I will see Fabian more often because he's also in the same work group as me. But you can join the random coffee break and maybe you end up with Fabian. You can always be lucky. Yeah, I see you then next week again. And thank you all for coming.
Thanks. All right.
Thank you.